All right, we have one final example here. I started it in the last video and got cut off again, so I'm going to start it fresh. All right, so we have the sequence 0, 3, 8, 15, 24, 35. And we notice that we are adding the odd numbers, starting with 3, to each of the previous terms in order to get the next term. And we know that in general, we can generate any even number by having 2 times, let's call it k, or we can get an odd number by doing 2k plus 1 or 2k minus 1. So for this sequence, I'm going to put it in a table again so you can see the pattern a little easier. 1, 2, 3, 4, 5, 6. We know 6 terms here. Term 1 is 0. Term 2 is 3, 8, 15, 24, and 35. Here we're adding 3. Here we're adding 5, 7, 9, and 11. You'll also notice the second differences are constant. So we'll come back to the fact that this is quadratic in a moment. That will come into play when we're talking about function notation in the general term. So for the recursive, we need to, in order to get term n, we need the previous term, and we add some odd number, but we're not sure which one yet. So looking at these, term 2, we had to add 3. Term 3, we had to add 5 in order to get it. Term 4, we had to add 7. So if we try 2 times n, or k I said before, but n in this case, plus 1, well, 2 times 2 for term 2 plus 1 would be 5. So that's an odd number that's too high. But if we add 2n minus 1, then that is correct. For term 2, 2 times 2 minus 1, so 4 minus 1, which is 3, we're adding 3. Term 3, we could check the same thing. 2 times 3 is 6, minus 1 is 5. Term 4, 2 times 4 is 8, minus 1 is 7. So we know that this is the correct, I don't know what to call it, difference, I guess, that we're adding. It's not a common difference, it's just difference. Okay, recursive. Term 1 is 0. Term n is term n minus 1, so the previous term, plus 2n minus 1. So this whole thing that we just talked about here. And n is greater than 1. This is the entire recursive formula for this sequence. Let's check it with one of the later ones just to be sure. Let's say term 6. We haven't checked that one yet. So that would be term 6 is term 5 plus 2 times 6 is n minus 1. Well, term 5 is 24 plus 12 minus 1 would be plus 11, which is 35. So we know that this is in fact correct. I'm going to erase this last little bit of stuff so that I have a little more room to write. We're going to go back to this. All right. Remember that table we just had, and we pointed out that it's quadratic. So knowing that, for part B, knowing that the second differences are constant, the pen really is not liking all this writing tonight. So it's kind of a mess, but we'll roll with it. All right, second differences means it's quadratic. So f of n is equal to, well, let's look at this. How can we get this? Perfect squares, 1, 4, 9, 16, 25, 36. You notice these are the perfect squares, but subtracting 1. So n squared minus 1, where n is an element of the natural numbers. This is our function notation for part B. So term 1 would be, f of 1, I should say, is equal to 1 squared minus 1, which is 0, so that's correct. Let's try f of 1, 2, 3, 4, 5. We have 6 of them here. Would be 6 squared minus 1, which is 35. So those are both correct. So we know that this is also correct. And then finally, the general term, I was going to erase, I'm just going to leave this mess of stuff here. Put part C squished over here. The general term is term n is equal to n squared minus 1. It's pretty much exactly the same thing here. We already know in sequences that n is greater than 1 by default, so this is true. And n is still an element of the natural numbers, also by default, so still true. So this is term n, the general term. And that finally, as long as that finally gets us through everything that you should know about sequences.